If my slide changes, yes, here it is. So I'm not sure if everybody's aware what CIMMYT is. So CIMMYT is one of 15 CGIAR centers. It's basically a partnership that between international research organizations that are engaged in research on food security. Okay, so CIMMYT is based in Mexico, so not as far from Brazil. And this has two mandate crops, so it's wheat and maize mainly, and does research and specifically breeding in these two crops. Okay. So just a little bit, the CIMMYT wheat program has been quite having some impact. You might know Norman Borlaug was kicking off the CIMMYT wheat program really in the 50s and received kicking off the Green Revolution and received a Nobel Peace Prize for this. So it's one of the most, I would say, or one of the biggest public sector breeding programs, especially for the Global South. And this is just a summary to an impact study, the latest impact study we did in 2016, what shows you the impact of the breeding lines. And you see that around 50% of the lines in the world have a CIMMYT either background or are a direct release. And a similar percentage of this is also true in Latin America. So pre-breeding, so breeding is in at CIMMYT's heart, wheat breeding, and as you all know, I guess already as students and maybe young scientists, is that wheat breeding today, or breeding in general today, is really a multidiscipline. It has multifaceted approaches. So one has to consider the different germplasm types, the different phenotyping technologies that are available today, high throughput screenings, but also trials across environments and regions, different methodologies, selection technologies, etc. And one area really also that has been playing a more prominent role in the recent years is really also the genomics area. And this is just a rough time scratch how the genomic tools in the last 2 years have been implemented in the CIMMYT Global Wheat Program. So especially this area, I think the advances were very fast, especially with sequencing technologies. So 20 years ago, when I even not started at CIMMYT myself, so most of the research in the laboratory was around biparental mapping, with hundreds of markers, maybe trying to identify certain genes related to certain traits. But today it's all about trying to push genomics outputs as fast and as cheap as possible into the breeding programs. And that is an exciting challenge. So really it's all about how to funnel really the genomics outputs that are more and more available into breeding improvement. And more recently, I would say the last 5 or 4 years, we are trying to more strategically address these questions. And we usually go from a trait, and then we decide, is that trait has thus a large effect, QTL or genes known. And if this is true, we go a very straightforward marker-assisted trait pipeline strategy to integrate basically these genes or QTL, but for the most of our traits, this is not necessarily the case. So for especially quantitative traits like yield, heat tolerance, drought tolerance that are so important for climate resilience, they do not often have this large effect QTL. So we need to find other ways to push the genomics outputs into the breeding programs. And often it's done through that relatively new approach, genomic selection. Also, there are still traits that we still don't know what is their genetic architecture. So one big examples and what is present actually in Brazil is, for example, wheat blast. We really don't know exactly what is the genetic base of this disease, important disease. So we are still in a discovery and validation phase. So just a little bit, just for the ones that do not work on wheat, I thought I'd give you a little bit of insight on the complexity really on the wheat genome. So it's really, wheat is the Mount Everest of plant genomics. It's really the elephant in the room. The genome is very, very big with 60 to 70 gigabases. So in comparison to rice, it's 40 times bigger than rice, and it's 6 to 7 times bigger than corn. Sorry. Okay. An additional complexity is that wheat is polyploid. So it's really, through its evolution, it went to 3 hybridization events. So it's basically a generation or an output of 3 different species. The first one is a Triticum urato, what is a diploid that was hybridized with this Aegilops speldoides species that is not really 100% known yet. What is the donor of the bee genome, we call it today. And the second hybridization was derived from a tetraploid species, with again that Aegilops tauschii, another diploid, to have today an allohexaploid species. So it has 3 genomes, 7 copies of each genome has 7 copies. So in total, 21 chromosomes that are large. And really, it was an extremely important and long-lasting effort to sequence the wheat genome. So at the beginning, it was kind of, is it a mission that is really impossible? But it was really an international collaboration, basically different international groups sequencing only 1 chromosome to get a first wheat genome sequence. And that is now available since 2018, and this is of huge help, certainly, in plant breeding. Okay, so going a little bit into the genotyping platforms. What is your topic today? So certainly it's not today. There are so many platforms and technologies available. So it's, at least in a public sector institution, it's not as such that we use just one technology. We use several. I think the biggest distinction is that we do is between low density genotyping platforms, so where really one or a few markers, molecular markers, are used on many lines, and it has its specific applications like quality control, but specifically marker-assisted selection. So examples are here STS markers, still some CAPS markers, SSR markers, but most of the time really SNP technologies, and the SNP technology of choice here is, I think, the CASP technology in wheat. On the other hand, we have the high-density genotyping platforms. So the difference really is that we have thousands of hundreds of thousands of SNPs per sample, so not only one or few, distributed across the genome. So we genotype usually fewer lines, but with many more markers. And applications are really mapping, GWAS, so association studies, diversity studies, line verification studies, or genomic selections, right? And examples here that we use at CIMMYT is certainly the genotyping by sequencing technologies, DART-seq, what is similar. We use Illumina SNP arrays, and others. So really, I thought I'm not going too much into the different technologies, but I want to raise the awareness of one that we have recently developed, and I do think that this type of technologies is probably what we will use in the future, and we have just developed this one. It's available through the Excellence of Breeding website that is linked to the CGIAR. It's a collaboration with the DART company in Australia. I'm not sure if you know that company. And it's basically a targeted amplicon sequencing platform. So what that means, it allows to, because sequencing is so cheap, it allows not to randomly sequence different bits or pieces of the genome. It allows to really sequence very specific targeted and selected area in the genome. So in this case, this technology is just a set of probes that are aligned to the DNA target. This target is then sequenced, and certainly through data processing, SNPs that are predefined are basically reported. Okay. So far we have developed such a .ag panel with around 3,900 SNPs that not only includes genome-wide SNPs, but it also includes our QC marker set. It includes genes and QTLs that we have identified in the history of CIMMYT genomics work, and it also has some connectivity to other genotyping platforms, so to kind of have an overlap between that and the importance of that. I will come back in a minute of this. Okay. This is just usually in the CIMMYT program. I will also explain this a little bit later when I go into use cases, what we really do with the genomics tools in the breeding program. So we have done .ag versus genotyping by sequencing comparisons, and we got really convinced by using or switching now to this new .ag platform or targeted amplicon sequencing platform, as we compared the two platforms for genomic predictions. So genomic predictions, what it means, you establish marker values for many markers and predict the breeding value of certain lines. And what we did see across many traits, that really the correlation between the two genotyping platforms, so the GWS usually we were kind of I think we have an output of 17,000 lines versus the .ag that has selected 16,000 SNPs, with the .ag in comparison around 4,000 SNPs. So the lower density does not seem to harm very much our prediction. So the correlations between the two platforms are really high. And not only that, also the lines we would select with the two different platforms are really similar. So we got quite convinced that moving to the .ag platform, what is less expensive and higher throughput, is allowing us to be a kind of a little bit more efficient. Okay, going back a little bit on the deployment of genetic tools. So in case we have really, genes identified and markers are available for certain genes, I think we have developed a pretty well-established, the last few years, trait development pipelines. And it basically includes three components. So first, the discovery component, what is certainly important to identify your genes and link your genotyping technology to it. Then we have a parental development component, what basically includes the validation of these genes or of our identifications in one or two CIMMYT elite backgrounds. And if the gene remains of interest and of high effect, this goes certainly into a line augmentation pipeline. So that means it's going to be crossed with several CIMMYT elite lines, and these are going to be distributed. So it goes kind of into mainstream breeding. Okay, so I will go a little bit into just some use cases on all these three topics. So we use for gene discovery, we still use very classical methods for our core traits. So one core trait really in wheat breeding is rust resistance. So we do still classical biparental mapping, especially for the three. There are three rust diseases in wheat that are global, that have global importance, and pathogens are involving very highly, and genes are often overcome. So really classical biparental mapping in some cases. We also do some biparental mapping for new traits. So one example here is spike photosynthesis in wheat. It's like this, that it has been shown in our physiology program that the photosynthesis of the leaves and the photosynthesis of the spike, you can see that in that graph here, that is an independent process. So it means that if we improve both photosynthesis levels, we can probably increase overall photosynthesis and with that grain yield. So there's also been effort to detect the genetic basis of these new traits. Certainly, then we use more and more genome-wide association studies. This is just an example from last year in our quality program. It's about arabinoxylan content. It's a group of polysaccharides that has an influence on dietary fiber, which have, on the other hand, a health benefit. So it's more about nutritional wheat. And we confirmed this QTL here on 1B, and we did show that markers we developed based on this GWAS hit do separate lines well that have high or low arabinoxylan content. Another example is more in the pre-breeding space. This is about drought and heat tolerance. So we still try for these complex traits to identify maybe genes not in necessary elite germplasm, but in germplasm that is more distant. So especially in wild relatives in wheat that could have the potential to be integrated into our mainstream breeding. And you see here a few examples also derived by GWAS that are linked to heat tolerance and that we are currently following up for parental development. Okay. Just going back to this funneling concept. So really there is so many QTL studies. If you do a Google search on any of your crop QTL or GWAS hits, so it gets too many that we are more and more getting lost. So many outputs. What do we do with this? So what do we do? Do we do with this? So what one approach we are also taking, what I just simply wanted to show is kind of deriving these QTL we call it QTL catalogue. Some others call it QTL atlas. So we are trying to align, and here are the genome sequences are so helpful, trying to align all of these hits we had in the past in our own germplasm on one common genome sequence, so that we can identify probably regions that are specifically under control or that influence many different traits. So each bar here basically represents on the chromosomes QTL hits or several QTL hits for different, in this case, yield component traits. Okay, I've just have a student here in my lab, Bachi Kasim, who is really trying to dive into some of these regions and say, okay, can we that way identify these kind of MetaQTL, we call them, and can we validate this? Is this an approach how to funnel basically the genomics outputs? And he's doing some good progress. Sorry, I go back. So this is just an example how he zoomed into this region. So we are trying to find establish different criteria for selecting these. First of all, they should have been they should be in low frequency in our germplasm, because we want to enhance our germplasm with these regions. They should have been identified by several publications or close to each other, and most of the regions he selected is kind of having multiple QTLs very close together and multiple effects. And we see in the validation phase that some of these regions are indeed do works. They show a good effect on yield. And what we usually do in CIMMYT to validate these QTL is just we run these across some germplasm panels that we have good quality phenotypic data on, and also genotypic data on. So we just add this information into our panel information for basically validation. Okay, so a little bit on the trait pipeline. So as soon as we have candidates really that we have established markers for, that we have established effect for, and that we know they have value or they have a defined value in our product profiles. Really, this goes into trait pipelines, into question pipelines kind of. And we have established recently in one of our research stations these rapid generation advanced facilities that are equipped with light and temperature controls to basically integrate these genes or traits very quickly. So here really with the marker technology, coming back a little bit to the topic of the day, is the CASP technology. Just simply it's quite cheap and it's very flexible to use. So it's a single Plex SNP platform that we can also very flexibly combine. So usually we do not do crosses only for one trait. It's usually every year we start one trait pipeline cycle. So it's a mix of different traits and mix of different crosses. So we can be very flexible to combine 15, 30 cusps across these trait pipelines. So this has been very useful for us, and we do not do necessarily run all these marker work in-house. We also use outsourcing, service providers to generate this data very quickly. Here it is. So usually what we do for the fully optimized production markers, we have a collaboration with Intertek, is a company I think is based in Sweden, that runs the cusp marker for us. So it's very fast turnaround time of 2 weeks, and multiples of 384 samples they process very easily. While in-house, we do some work in-house, still the old markers that we have not been able to convert to a SNP system. This is still, some markers are tricky in wheat, just because of the polyploidy, mainly because of the polyploidy, but also others are very complex to run. So then, the service providers, they do, it's really good to use their throughput and their highly optimized technology and automated pipelines. However, for more complex products, sometimes we prefer really to run it in-house, because we have the flexibility to repeat some of the markers if they are giving not good results. So we are more flexible in running them. So usually it's a mix between in-house and outsourcing technologies. So this is just a quick overview how we integrate these genes. So usually we do 1 or 2 back crosses, and up to this stage, so the back crossing and the crossing is done in the screen or greenhouse. So for rapid generation advanced, so we can go one cycle in 3 or 4 months. And then the field testing is basically done in the field stations. This is just some priority traits in case you work with wheat. You can maybe identify some of the genes, but really following right now is we are following a lot of rust genes, so disease-resistant genes, also other wheat diseases, Fusarium head blight, I think it's also important in Brazil, Septoria, Triticale blotch, but also starting with some more parental development from some of these outcomes I showed you before from this mapping of the yield components. Okay, I think I skipped this. This is just, yeah, okay. So coming to a little bit my last topic. So when we use, so really in the marker-assisted trait pipelines, these low-density genotyping platforms and mainly CASP is used. So this is not very helpful for approaches like genomic selection. Here we fully use genotyping by sequencing at the moment, with the goal, what I mentioned before, to move to the targeted amplicon sequencing approaches like the DART-AG platform. This is just giving a small overview where we apply the high-density genotyping platform. So this is a very simplified version of our breeding program. So we go into the crosses. The line development is basically selfing stages, and we first genotype our lines, what we call PC, Parcela Chica, in Spanish. And it's where basically these are small observation plots where the breeders go through and basically looks only at the performance of the plot, of the line, maybe plant height, maybe heading, but not really, data are not really recorded. So these lines are currently, and these are around 20,000 lines every year. These are fully genotyped, and we use these lines together with the visual observation to discard basically the lines that do not do very well. Okay. Mm-hmm. So what we do, so usually the process is that these small plots, so the lines selected go into first yield trials. So here we have around 4,500 lines that are now fully tested for yield and other traits in more than 4 environments in our stations. These go then into the second yield trials, again, 600 to 700 lines, testing now in more environments and more traits. So what we do, we use these data from the first and second yield trials to predict basically the values of the next cohort in our small plots. And these data then, so these predicted data helps us to discard about 60 to 70% of the lines. Okay, so this is just how this kind of a little bit looks like. This is now some prediction accuracies in our first yield trials in this stage. So here we have one yield measurement, but also we have the predicted yield, and you see, usually we get correlation around 0.4. And this helps to say, okay, we do these thresholds, we say, okay, these are the lines that are badly predicted and they have bad observations, so we can be pretty sure that this can be discarded. And these are just some correlations between the observed and predicted values for these other traits than yield. So this is really where you use these data to estimate the value. So in this case, estimate these values for the lines that are not at all phenotyped, and you see that some of these correlations are quite high, especially what we see over and over again for quality parameters and also some disease parameters. So the predictions are really, really good. So we can easily, or with high confidence, discard lines that are, for example, susceptible. Okay. So the goal really is here to go faster in the breeding cycle. So we are optimizing currently, or in optimization of changing our breeding scheme. So one component in the formula of reaching genetic gain in plant breeding is time. So as faster we go, so as faster we recycle, as faster we can make progress. But the drawback is that as faster we go, we use certainly precision, right? Because we do not have as much data on the lines to say, okay, this is my best lines, and I use it in the next cycle as a new parent. So it's a game between precision and time. And this is just a scheme how we want to make use, especially on our facilities now in one of the stations. So the idea is to go quickly, more quickly through the first really early years of line development, then only 1 year testing, and the parents will be recycled. And we want to bring that to an extreme. So there is research ongoing in the institution or in my team that really wants to bring that in extreme. And one concept is really rapid cycling, recurrent selection, so that we very early use the genomic information to select parents even without being phenotyped for a new crossing cycle. And we did this small proof of concept experiment where we recycled basically F1 lines 3-4 times without any phenotypic evaluation. From each cycle, we extracted a number of lines, and we evaluate these lines in the field together to see if we had really made some progress. And the target trait here was also yield. And not sure if we were lucky or not, but we did saw an increase in overall grain yield across the cycle. So recycling the F1s, the breeders are still reluctant to test these further, but we could show that we got indeed some yield increase by recycling very fast over and over again. So these are really technologies where it's poorly genomic, and it seems to have potential. And this is something that we are definitely going to be exploring in the next few years much more seriously. So one issue in terms of genotyping technology, I wanted definitely to raise, and you are, I guess, the guys who can maybe solve these complexities. You have new skills that maybe my generation does not have yet. So we really need some solutions, especially in the data space. So really big challenge is that as we are public breeding program, so we are based on really different projects. So we have to so we are project structure. So we have funds from different donors, and we are collaborating with different institutions. And what that has been led to is that what I mentioned at the beginnings, we do not use only one genotyping platform, but we use many. So now we have really the struggle that we have big data across different genotypes with different platforms, and we have a really hard time to bring the data. Can we bring them all together by aligning them, for example, to a sequence? So this, for us, we need to start working on this, but it's a big challenge, and we could probably do even a higher data or bigger data analysis if we could combine genotyping outputs or genotyping data, combine them together. So just an example, our gene bank accessions, most of them, there's been a big project at CIMMYT to evaluate the gene bank. It's one of the biggest wheat and maize gene banks in the world. So about 90,000 accessions are genotyped with this GBS start-seq technology. However, most of our breeding and pre-breeding lines are genotyped with a different GBS platform, right? So bringing this together would be very powerful, but it's very complex. This is one solution we are following. I'm not sure if you heard about this, practical haplotype graph, where basically the genotypic, where basically sequence data is used to define common haplotypes, and the haplotypes are aligned. The haplotypes are in some of the, or revised with some genotyping exome capture sequencing technologies, to which we then assume we could align our SNP callings from lower density or lower density sequencing platforms, and then basically impute common haplotypes. But this has been challenging just because of the computational space, or the depth of the computation is huge. So we have been trying to extract these haplotypes, but it has been taking more than a day for one line. And if you have to basically analyze 20,000 lines, it's just not feasible. So we need definitely different solutions. With this, I want to close. So I hope I could show you that the genomics technologies are definitely increasing, deployed also in complex crops like wheat. It has been it's an extremely important discipline in breeding right now. Diverse genotyping platforms are available and they are known, and I think it's still the cost and maybe the availability of the bioinformatics and biometrics pipelines each institution has is probably the main factor that drive the deployment. So often, in our case, in the public sector space, there is one platform is used. This might be different in the private sector, where they can push, certain platforms or decide on certain platforms across crops. So this is more difficult in the public sector. So the validation of the genomic outputs, I think, is one of the most time-consuming. So genotyping is not an issue today anymore, but the validation of the outputs and funneling these outputs, I think, is the most time and costly exercise today. And it's really the rate and speed, how you can adapt these genomics outputs that drives the impact in breeding. Phenotypic evaluation is still key. I think we are very aware of that, and especially evaluating different germplasm. So this should not be forgotten. With that, I just mentioned, our fundings and some people where I showed really slide of so CIMMYT colleagues and breeders in the wheat breeding team. Thank you. I think the questions will be addressed later, I understand.